Dear Chairman, dear colleagues, first of all I would like to express my gratitude for this opportunity to have a talk today. My name is Timur Shankulov and I am representing the Laboratory of Biomedical Informatics at Burdenkoner Research Center. We have done research on the classification of short scientific texts using text statistical features, and we want to share our results with you. Screening articles related to a specific subject is the most time-consuming stage when analyzing the literature. Following the entire amount of publications, even if one professional domain, is impracticable. How can we simplify screening or tracking publications relevant to any research? Automated text classification methods could significantly facilitate scientific literature appraisal by researchers, especially in systematic reviews. The scientific abstract selection could be approached as a binary classification task. Thus, the collection of short texts is divided into two classes: relevant, for example, related to the topic, and irrelevant. This research aimed to test the quality of short medical abstracts classification, primarily based on text statistical features. If the approach proved efficiency, we might consider text statistics for inclusion in ensembles with machine learning models to improve the short text classification quality. The dataset for experiments was obtained from PubMed while performing a systematic reviews of artificial intelligence applications in the researchery in July 2019. The publications obtained with search query were manually divided into two classes. An article was assigned to the first relevant class in accordance with shown criteria. The second irrelevant class contained all other publications which did not meet these requirements. The basic text statistical features we considered were the following. At the first stage of our experiments, we calculated the set of character statistics, word statistics, and statistical ratios. At the second stage of our approach, we added the keyword statistic to the training subset. And at the third stage, we added three-dimensional word-to-vec vectors to the above-mentioned features. We split word-to-vec vector values into three columns and handled them as the separate features of the subset. Character statistics were the number of symbols belonging to a specific distinct set. Word statistics were calculated on a higher level of document entity, words and sentences. Statistical ratios reflected the ratios between the various text statistics. We selected the list of ratios for the classification task. Keyword statistics representing the occurrences of predefined keywords. Having expertise in the subject domain, we were able to add some keywords as the features to machine learning models. We used 4 machine learning models for the binary classification of abstracts at every stage of our approach: random forest, logistic regression, supervector machine, and naive Bayes. Thus, a total of 12 classification approaches with various parameter sets were utilized. Each experiment with one machine learning model applied to a specific set of text statistical features was repeated 300 times with automated resampling to estimate the average classification quality. The number of combination of features were different in distinct tests. In each experiment, the training subset was randomly sampled as 80% of the initial dataset, while the remaining 20% were used as a test subset. Automated sampling stratification was applied using the sklearn Python package to keep the subset class balanced. The total number of tests performed were 3,600. Here is a set of tools that we used to do all the calculations. We applied Python 3.8 within the Jupyter Notebook IDE. A total of 630 articles were manually assigned to the first and the second class prior to experiments. The result within each test series of 300 tests were averaged for each of 12 classification approaches with different parameter sets. The major dataset characteristics are shown in this table. The mean text length was about 1,600 symbols, with the average number of words around 130. The average classification quality for the 12 experimental series are demonstrated in the table in descending order of F1 score. The type of machine learning model is presented in each row: RF for random forest, NB for naive Bayes, SVM for support vector machine, and LR for logistic regression. The keywords label indicates if the keyword statistics were used within the classification approach. The word-to-vec label shows whether the word-to-vec embedding dimensions were added to the text statistical features. The best machine learning result was achieved by using a random forest model with keywords and word-to-vec components added. Random forest model without word-to-vec elements achieved F1 score equal to 0.76. Thus, adding word-to-vec as a feature increased the classification quality with a random forest model by 1%. The result of our study demonstrates that the automated classification of scientific abstracts could be accomplished by using relatively simple and computationally inexpensive methods. This approach allows the implementation of text classification even if only a small dataset is available. It doesn't require high-performance servers with the graphic cards. We didn't fine-tune hyperparameters for machine learning models during the test, using the defaults provided by Scalone Python package. This allowed us to focus mostly on data preprocessing and feature engineering. We expect that models fine-tuning will improve the classification quality. In our future studies, the new text statistics would be tested and hyperparameter of machine learning models tuned. We consider testing new machine learning models, also in ensemble design. For instance, a high-performance topic memory network might be such an option. The classification of short scientific abstracts might be implemented using the approaches described in this paper. These methods are expected to facilitate the selection of literature by researchers, potentially increasing their productivity and research performance. I am glad to thank my colleagues from the Laboratory of Biomedical Informatics and Artificial Intelligence and Burdenkin Research Center for their help and contribution to the project. If you have any questions, suggestions, or if you want to contribute to that project, please do not hesitate to contact us.